So welcome to my second video on electronics projects, electronics design. Do any of you recognize what this is? Or I guess I should say more importantly, what it was. Well, let me show you. This is what it was. So obviously I made a few modifications to that, and because I didn't like the way it performed. What it was these two fans were on the side, and they were both blowing either forward or backwards. So if you wanted to go forward, they both pushed forward, or both pulled backwards, and then alternate to, one forward, one backwards to turn right or left. You could not use differential torque on the main rotors like they do on newer ones today, because these are both linked together through one motor. So the torque balances out. In fact, you actually, by turning this yellow knob at the top, you're tweaking the pitch here to increase or decrease the drag of the top rotor to make it stay steady. And then to make it turn left or right, you would put one forward, one backwards on the motors here. The problem I had with that was that when you're going forward, they're both pushing forward. It seemed like one motor blew just a little bit harder than the other, so it would go forward and turn as it went. Plus, given the fly bar here, trying to make it stable, it's like it would go forward and it would just really slow down and stop and almost not move at all. So it just did not handle very well at all. Now this thing is old. Most of you, I don't know if you remember what's it called, the reflex. If you remember the reflex, yeah, these things are ancient. They never flew very well at all. It has other issues. For example, when you would go to turn on the little motors here to go forward or backwards, there was like a half a second time delay. So anyways, way back when I got this, probably, I don't know, 10 years ago, I was just starting to get into using surface mounted components. So I decided to use this as a test project for using surface mount components. My idea was to move the two fans here back to here. So if I wanted to go forward, this fan would turn on, lifting the tail to go forward, or spin the other way to push the tail down to go backwards. And if I wanted to go left or right, then only this fan would come on to turn it left or right. The problem here is that on normal operation, both fans are always on. Either both fans are pushing forward, or both fans turning back, or both fans, one spinning opposite direction from the other to make it turn. So I needed to make a circuit to change the normal operation into the new operation that I wanted. And that made this circuit board right here. Now I have one surface mount IC on that side, and I have another surface mount IC on the other side. And again, I did not do this because I wanted a nice helicopter to fly. This flies like garbage. I have other helicopters that are much nicer to fly. I did this as an experiment for a functional application for working with surface mount ICs. And again, this is probably like 8 to 10 years old, somewhere around there. Now you'll notice I have a jumper wire here, one on the other side. That's what happens when you don't perfectly plan the circuit board. I had two lines crossed, so I had to cut two traces and resolder on new traces. But again, not that big of a deal. And you'll notice, this circuit board is extremely simple. One IC here, one IC on the other side, and my website, bluerayscars.com, is etched on there. Again, this was more practice for etching circuit boards, so this was just a practice board. I was trying out a new technique for etching circuit boards, soldering on surface mount components. There's a little connector here so I could just unplug it. So I have the motor outputs from the main circuit board coming in, then I have wires going out to the new fans. So again, my point for this project, and I'll try to fly this at the end of this one. I haven't flown it in probably 7 or 8 years or more, but I got a battery and a charger. You'll notice my battery holder. I have to put the battery way out here to balance it, because since I moved the fans back here, it got really tail heavy. So I have to have the motor way out here to balance it. And that was another issue. It just looks stupid while it's flying. But I got the battery and a charger. I don't know how good that battery is, but we'll see how it goes. I'll try to take this on a short little flight just to demonstrate it. But the point of this video is to talk about logic circuits and how to design a circuit using logic gates. Okay, because I used some logic gates here, and that's all these ICs are logic gates. So let's get started with that. For logic circuits, there are 3 basic logic gates. For example, the first one I'll put here looks something like this. And this is what we would call an AND gate. Now, everything on this side is going to be inputs. You can have as many inputs as you want. I only drew 2, but you could have 100 inputs. So this side of the gate will have multiple inputs. This side of the gate will always only have 1 output. And when we say AND, what we mean is in order to get this output, we need that input and this input. And when we're talking about inputs and outputs, I'm specifically talking about, typically we use ones or zeros, okay? When we talk about 1, you can think of a 1 being positive voltage. You can think of a 1 being maybe true. You can think of a 1 being high potential, or you can think of a 1 as being on. With a 0, you can think of that as being a negative or a low potential, or false, or off. Basically, power or ground. You can think of that as well, power or ground. Okay, so we could put power or ground. So those are what we think of when we use 1s and 0s. Okay. So for an AND gate, in order to get the output, I need all inputs. So in order to get a high output, I need this input to be a high. I need this input to be a high. Then I will get a high output. That is the only way to get a high output if all of the inputs are high. So we need every single input. Think of this as mechanical switches wired in series. Okay? If you have power going through a switch and another switch, and then finally an output. We'll just put a light bulb here. In order for that to come on, this would be the 2 inputs, that would be the output. I need that switch and that switch. Okay? The next gate is called an OR, and I always draw crappy looking OR gates. Again, that would be an OR. You can think of an OR gate as switches in parallel. So in order to get a high out here, I need this one or this one, or both. So in order to get a high here, I need this one or that one. It doesn't matter. Either one or both. Think of this as switches in parallel. So if I had power and then a switch, and let's say I have power here and a switch, and those 2 switches come together to a light bulb, I need this one or this one to give me the light, or both. Now, one thing that a lot of people have a hard time with when they're looking at gates is determining which one is which. Like they'll see a logic gate, but they can't remember if it's an AND or if it's an OR. That's probably the most common. Part of my profession is I teach this at a basic level to aircraft technicians. And again, I teach it at a very basic level the way I teach it here. And most people, what I see in a classroom, most people have a hard time remembering which gate is which. This is what I did way back in the day when I first started playing with this for a hobby. It's kind of corny, but if you do this, okay, that's a D for the AND. Now that doesn't look like an R, but if it's not an AND, it's an OR, okay? The other gate, the other logic gate, just looks like this. This could be called a yes gate, or it could just be called a buffer. Sometimes it's just called a buffer. What this does is if you put a high in, you get a high out. You put a low in, you get a low out. And you might be asking, well, why the heck would we use this? Well, this could give us a stronger signal out. So if you put a really weak signal in, you can get a stronger signal out. Okay? Again, it's a buffer. It just it strengthens a signal. It Depending on the type, sometimes they can amplify the signal. Okay. These are the three basic gates. Everything else that I'm aware of, like I said, I'm no electrical engineer, but everything else that I'm aware of is just what's the word I'm looking for? It's just a change of these gates. It's a modification. That was the word I was looking for. Sometimes I feel like English isn't my first language because simple words, they just kind of, they leave me. So every other gate is a modification of one of these. Now, the most common modification is a little circle. For example, if I take the yes gate, if I just take that yes gate and I modify it by putting a little circle right here, that now becomes a not gate. That basically becomes an inverter, meaning if I put a high in, I get a low out. If I put a low in, I get a high out. And you can put that little circle anywhere you want. Okay? For example, I could put that little circle at the end of an AND gate. So if I start off with an AND gate like this, and I put that little circle right here, I basically just made a not AND, or what they call that is a NAND. Okay? A not AND or a NAND. And again, like I said, anytime you see that little circle, what you have to do is think about what you should have and then flip it to the opposite. So for example, if I put a high here and a high here, well, that should give me a high here. But I have to invert that to a low coming out. So if I put two powers coming in, I have a ground coming out. Now I can also modify the OR gate. So if I make another crappy looking OR gate, put the two inputs here, and I put that little circle here, now I made a not OR or a NOR. So again, if I put a high on one of those legs, it doesn't matter what the other leg is because it's one or the other or both. So as long as any one of those legs is high, that should give me a high, but I would have to invert that to a low. Okay, so anytime you see that little circle, think about what you should have and then invert it. Now there's another variation to the OR gate. For example, again, I draw my crappy looking OR gate, but if I put another line like this, that now makes it an exclusive OR. If you look back up at the OR gate, an OR gate is one or the other or both. Okay, one or the other or both. This would be one or the other, but not both. So if I made that leg high and that leg was low, that would give me a high out. But if I made that leg high and that leg high, that would give me a low coming out. So again, an exclusive OR is one or the other, but not both. These are good for comparing inputs. So if you have two inputs coming in, as long as both inputs are the same, if they're both high or if they're both low, you got a low coming out. But as soon as one of them is different, it now becomes high. So this is good for comparing two bits of information. Okay? So as long as they're the same, we get nothing coming out. As soon as they're different, we get a high coming out. Now you could also have an exclusive NOR by putting a little circle right here. Now remember I said you could put that little circle anywhere you want it. You may see diagrams drawn like this. You may see a circuit that looks like this. Okay? That's an AND gate with an inverted input. That is the same thing as doing this. That's the same thing. That's just a shortcut for doing this. Okay? That would be like putting an inverter on one of the legs. Sometimes people draw the whole inverter, sometimes they just shortcut it like that. It all depends on who's doing the diagram. Now, one thing, again, I talked about things that kind of trip people up, and one was remembering the difference between AND or, and do that, that'll help. Another thing that I've had people tell me kind of trips them up and they have a hard time understanding is, how does a gate make power? Okay? And when I was first asked that question, I didn't quite understand where they were coming from. And then he said, well, for example, if you look at the NOT gate, let me just draw another NOT gate over here. Draw the NOT gate. He said, well, if you put a ground on this side, low potential, that gives you a high potential coming out over here. How does that make power? And then it kind of dawned on me as far as where he was getting at. And the thing is, when you're looking at these diagrams, the people who draw these in electrical circuits, they don't give you the full story. For example, this has power here and ground here. They all have that. This has that. They all have that. So all of these gates are powered circuits. Okay? So it's not creating power. It's just looking at that ground and sending that power out. If you put a 1 here, it would see that high and it would send that ground out. So all of these are powered circuits. Now another thing that trips people up is, and especially technicians, people who work with their hands and turn wrenches, and a lot of us technicians we're physical people. We need to see things. We need to see and touch things in order for it to make sense. These pictures I'm putting on here, well, like this one right here. Everybody can look at this and say, oh, that's a light bulb, right? You look at that signal, that symbol, you say, okay, that's a light bulb. Everybody knows what a light bulb looks like. And if I were to draw a symbol like this, most people would see that and say, okay, well, that's a resistor. We know what a resistor looks like. If I handed you a printed circuit board and said, show me a resistor, or point to a resistor, most people could do that. But if I handed you a circuit board and I said, point to that OR gate on that board, most people wouldn't know what to point to. This is just a symbology of the logic. The actual component on the board could be several things. It could be, that could be just a few transistors wired up in parallel, or transistors wired in series. It could be a dedicated IC. For example, I showed this pack on a previous video, and it could be, if I can pull that out of there, it could be on an IC like this. Now, any one of these ICs could have like 4 logic gates on it. In fact, if we look at the back here, we take a look here, we could see what's on each of those ICs. And again, they're not showing us all the pins, because you'll have 1 pin for power and 1 pin for ground. And the power goes to all of those gates. The ground goes to all of those gates. So again, the logic could be on an IC like this. The logic could also be just on a processor. You could have a board with a processor on it, and the logic could be nothing more than software that somebody programmed. So again, when you're looking at these symbols, it could be a physical thing like transistors or an IC, which, by the way, on the IC, inside of that IC, there's just a bunch of transistors. Those logic symbols, or those logic gates, are just made out of a bunch of transistors wired in series or parallel. But again, it could just be software that somebody programmed. So again, hopefully this is helpful for you to kind of understand better what logic gates are for, the symbols, how to remember the different ones. But what I want to show you now is how to actually make a useful circuit out of this. Okay, so back to my helicopter. Okay, if we take a look at what's going on with this helicopter here, the main printed circuit board. Okay, the main board here, so we'll say this is the existing printed circuit board, had wires for one motor, and it had wires for another motor. And to go forward, for example, and we'll just kind of do like a truth table. So we have forward, we have reverse, and we'll go turn left and turn right. Okay. So for forward, and let's say, and I'll just keep it straight down this way. So for forward, we'll say that this wire would be positive, that wire would be negative. And then same with the other fan, positive and negative. So they're both turning the same way to go that way. For reverse, well, we're just going to reverse the polarity of those two motors. If we want to turn left, then, and I forget which one is which. I'm kind of just making stuff up now. I designed this circuit like 10 years ago, and I looked for my original diagrams. I can't find them anywhere. So without actually metering out everything, I'm just kind of making stuff up now. But let's just say to turn left, we want this one to say be that way, but this one would be opposite, and to turn right would be the other way around. Okay, like that. The problem with this is, for the setup I want, is both motors always turning at the same time. I want one motor to turn at a time. So what I want, so this is how it is, what I want is when I go forward, I want one motor to blow forward and the other motor not even be on. To go in reverse, I want the other way and the other motor to not even be on. To turn left, I want that motor to be off and this one on, and to turn right, that motor off and that one the other way. So in this case, I only want one motor running at a time. So I have to build a logic circuit to make it do that. Okay, so this is my basic truth table on what I need. So what I need then is, I have two motors, right? Let's just start off with, let's say let's try to do this with AND gates. I'm going to draw the AND gates this way. So there's one, yeah, I kind of screwed that one up. 2, 3, 4. And let's say I want these two AND gates to drive one of the motors. Let's say I want that to be the forward reverse motor. And let's have this one drive the left and right turn motor. So when I want it to go forward, and of course have the legs for the AND gates here. Let's just look at one function at a time. When I want it to go forward, let's say I want this gate to be positive and I want this one to be negative. So I have to turn on that gate when I want to go forward. So what I would do then is I would look at whichever one here. I would take this one. I would take this one. So to go forward, I need positive. So I need this one would come down to here, and this one would come down to here. So when I go forward, those two would give me the high out here to give me the power. Okay, this one would be a low potential because I wouldn't be making those circuits. And when I want to go in reverse, well, it would just be the other ones. So I would take this line, take this way, and this line to here. So then when I go reverse, those other lines that would then be positive will give me this gate. This one will be off, giving me a low. When I want to turn right, or let's say when I want to turn left, then I'm going to take this one, this leg that's high, and again I can just tie off here, and I could take it to one of the legs, and I could take on the left turn this one that's high, say this one, and go down to the other leg. And then when I want to turn right, well, I take this one that's high for right, and I go down to here, and then I take the other one here, which would be this one. This is getting really messy now, to here. So now, whatever way these are energized will go to the appropriate inputs to give me the individual motor. And I really hope this makes sense because this got really messy here. And this might be the messiest way to do it. There's other methods to figure this out, okay? But this should work. But there's a problem here. If you remember on the IC that I made, I actually had, or on the circuit board I made, I actually had two ICs. Now one of those, this one is all of this right here. So those 4 AND gates are on one IC. Those 4 dual input AND gates are all in that IC. If you remember, I've got another chip right over here. See, here's the problem with the way I drew it right now. The output of that logic gate is not good enough to drive that motor. Okay, it just can't handle the current needed to drive that motor. So what I need is some form of a motor driver. What I used there were buffers or yes gates. So if I put a gate here and here, so I have 4 buffers, and what they can do is take a weak signal in and give me a stronger signal out. Now there's various part numbers for that, and you have to look at the IC data sheets to see input voltage versus output voltage and current. These particular buffers were designed to provide a higher current to drive things like motors. So that's one IC, that's the next one. Okay, so this is just a fairly simple diagram of, again, it was just a practice, just to experiment with, play around with, and it was one of those things where if it didn't work, it's like, who cares? Because this thing was kind of junky anyways. So it was just more practice for me to build a small board and use surface mount components. And again, I screwed up. That's why you see those little jumper wires on there, because I got 2 of those crossed when I drew my circuit board. And so when I think when I went forward, I'm trying to remember what happened. I think when I went forward, it went forward and turned at the same time, but everything else was fine. Something stupid like, I don't remember exactly, but something like that. Okay. All right, now, like I said, I really got messy with this, but hopefully you can understand how we can use logic gates to take an input and change it to give a different output, a more desirable output. Okay. So I've got the battery charging, so let me see how that battery's doing, and we'll see if this thing still flies after it's been setting in the corner for the past 10 years. By the way, if you have any questions here or any other comments, feel free to put them in. But if any of you are new to electronics, you're just getting into it, you're just beginning, I am definitely not the only source. There's countless websites, countless YouTube videos that go through all of this, different ideas, different perspectives, different views, but hopefully something I said here can be helpful. Sometimes when I'm learning something new, I'll watch 3 or 4 videos and I'll pick up something different on each one, and you put that all together, and that kind of completes the puzzle. Like the guy who said he didn't understand how they made power. As soon as I explained that, it's like everything just clicked. Everything made sense. That was the last piece of the puzzle he needed for everything to make sense. So again, hopefully something I said here is helpful. Hopefully you understand my scribbling here and kind of give you an idea. I don't expect anybody to copy this circuit. I mean, you can if you want. You don't even have to give me credit. But anyways, I'm rambling again. So let me go get the battery, and we'll see how this thing flies. Now there is one more gate I'll mention. I was debating whether I wanted to bring that up or not, because if not used right, it could just get a little bit messy. And you've got the AND gate, you've got the OR gate. The other one is called the butt gate, and a symbol, it just looks like a big letter B for butt, for the butt gate. And what's unique about this is it only has one output, but instead of like the AND and the OR, where the output is either a 0 or a 1, instead of a 0 or a 1, this only outputs 2s. So anyways, use that as your discretion. All right, we'll try to fly it. I really don't think I'm going to get the whole thing in shot as it's flying. I'll reposition the camera later. But even if I can keep it in view, I don't know how well you're going to be able to see how the motors actually affect it. So I'll just show you this first here. Here's forward. And you can see it lifted to tail up a little bit. Here's backwards. Again, notice only one motor's coming on. So then forwards, backwards. So you can see it working. And here'd be a right turn and left turn. And again, there's a little bit of a time delay. When I first push the stick, a little bit of a time delay before it actually comes on. So that makes it a little bit tricky to control. And plus on this, there's no trim. So if it starts kind of spinning out of control when you take off, you can't trim it. Once it starts going, it just wants to climb like crazy, so it's hard to keep it off the ceiling. But let me reposition the camera. Let me see if I can get some views of this thing actually trying to fly. And I think I'm going to have a hard time keeping this in frame, but I'll do my best. Come on. Oh, and I think my transmitter batteries are kind of weak. I've got to be really close or it just shuts off. Let's see how it goes here. Ah, what the heck. Yeah, I think it got too far away. Let me see if I can find a new battery for my transmitter. Okay, let's try it again. Hopefully that's in frame. Ah! I don't know. That didn't sound good. So I'm not quite sure why it kept cutting out. I don't know. I mean, it is old. The battery's probably not that good, but seems like it's just kind of losing the signal. But it may be just time to retire it and see if the Smithsonian wants it. Oh well. One more thing I just thought I'd like to answer before you had the question. And I didn't really explain how I knew how to use AND gates. When I very first started trying to figure this out, I didn't know exactly what I needed. And if I remember right, I think I tried different combinations of gates. And this is just what I came up with. It's just a little bit of trial and error and experimentation. And sometimes that's what it takes. Just got to think about it and try a few different things and come up with something that works. So anyways, sorry I didn't get a really good flight to show you, but the point of this wasn't to demonstrate my awesome flying skills. It was to talk about uses for logic gates. So anyways, hope you got something out of that. Hope you enjoyed it. And as always, thanks for watching.